We have started the F block elements, right? So after going through the electronic configuration, oxidation state and the ionization enthalpy, we will discuss the color of the lanthanoids, right? So as you know now that the general electronic configuration of the F block element is n minus 2 F 1 to 14, gradual filling of the F subshell or F orbitals from 1 electron to 14 electrons, n minus 1 be 0 to 1 and ns2. Since the last electron enters in the F subshell, they are known as the F block elements, right? So the lanthanoids. So we have got F blocks, two groups of their lanthanoids and the actinoids. So the lanthanoids, where here there will be gradual filling of the 4F subshell, and another is the actinoids. There will be gradual filling of 5F subshell, which we will discuss later. So the lanthanoid is a gradual filling of 4F subshell, and the element starts from the lanthanum, right? And its atomic number is Z equals to 57, to lutetium Lu Z equals to 71. These elements, lanthanoid and actinoids, you know that is known as the inner transition elements. Now students, we will come to the next characteristic of the lanthanoids, that is the color of the lanthanoids. Generally, the lanthanoids, they are silvery white metals, right? Except the trivalent ions. Right? So the trivalent ions, where we have the lanthanoids uh, in the state Ln3 positive state, there these ions, they are colored ions, right? And why they are colored? Because there they absorb from the visible light, right, suitable frequency radiation, and the electron will jump from the ground state of F subshell to the excited state, that is, there is FF transition observed. So the lanthanum tripositive ions, they are colored ions due to FF transition, right? FF transition in partly filled F subshell. So students, there the F subshell is partly filled, and hence you will get the FF transition observed, right? And the energy that will be the particular wavelength light that will be absorbed for this, its complementary color will be transmitted. Right, students? This is about the color of the transition, color of the lanthanoids. They are silvery white metals, general, but in their trivalent state, they are going to be colored iron, and the color is because of the FF transition which has been observed. Now, student, the next property of it is the magnetic properties. So the magnetic properties of the lanthanoids is attributed to the electronic configuration of their F subshell. If the F subshell is incompletely filled up, or it is partly filled, right? Or we can say that if it has got the unpaired electrons in it, that time it will be a paramagnetic substance, right? And if we have the completely filled up orbitals or the empty orbitals, it will be a diamagnetic substance. So the magnetic properties, so generally are paramagnetic, right? In the state, if they are +3, we are assuming here +3 state because that is the most common oxidation state of the lanthanoids, right? The paramagnetic, generally are paramagnetic due to presence of partly filled, or we can say unpaired electrons in f orbitals. Now here except we have, if we take lanthanum La3 plus, it has got F0 configuration, and if we take lutetium 3 plus, it has got F14 configuration, right? And if this is a state, then they are diamagnetic in nature. So the paramagnetic property will depend on the presence of the unpaired electron in f subshell or f orbital, and if they are completely filled, or if any of the oxidation state have got the completely filled uh, f subshell or empty filled f subshell, they will be diamagnetic in nature. Right, students? So this was about the magnetic properties of the lanthanoids. Now, students, next we will talk about the chemical reactivity. So here, the next is the chemical reactivity of the transitions of the lanthanoids. So lanthanoids, they are highly electropositive metals. Lanthanoids are highly electropositive metals. Right here. So, okay. So highly electropositive elements they are, right? And their electropositivity makes there is very less difference in their. So lanthanide are highly electropositive metals, right? And these have similar chemical reactivity, and which make it make their separation difficult. Right, students? So the chemical reactivity, lanthanoids are highly electropositive in nature, electropositive metals, and they have got similar chemical reactivity, and that's why their separation, right, of their compounds becomes very difficult, right? So here the only difference between these elements are going to lanthanides will be only the difference in the number of the 4f electrons, right? So they differ from one another only in the number of the 4f electrons, and the interaction of the other element with these lanthanoids, right? It has been shielded by the presence of the 5s, 5p, and 6s electrons. Right. So here you have to keep in mind that their separation is difficult. Why? Because of their similarity in the chemical reactivity, and which is mainly because mainly reason is due to their, we can say, the number of the 4f electrons only difference is there. Rest they are almost similar in their atomic sizes also. This we will discuss when we will studied about the lanthanide contraction also, which give them the similarity in their atomic sizes, right? Next is the basic nature. Next is the basic nature of the lanthanoids